Our goal in this video is to design a way of keeping the height of our binary max heap shallow. Well, what is a natural approach to create a tree out of n given nodes whose height is as small as possible? Well, it is natural to require that all the levels are fully packed, right? This leads us to a notion of a complete binary tree. By definition, a binary tree is called complete if all its levels are filled completely, except possibly the last one, where we require additionally that all the nodes at this last level are in leftmost positions. Let me illustrate this with a few small examples. So this is a complete binary tree. This is also a complete binary tree, and this is also a complete binary tree. This is a binary complete tree too. And this is our first example of a binary tree which is not complete. Well, it is not complete because on the last level the two nodes shown here are not in the leftmost positions. This is also not a complete binary tree. This binary tree is also not complete because, well, this child is missing here, right? And this is also an example of a binary tree which is not complete. The first advantage of complete binary trees is straightforward, and it is exactly what we need actually. Namely, the height of any complete binary tree within nodes is big O of log n. Intuitively, this is clear. A complete binary tree within nodes has the minimum possible height over all binary trees within nodes. Well, just because all the levels of this tree, except possibly the last one, are fully packed. Still, let me give you a formal proof. Well, for this, consider our binary tree and let me our complete binary tree, and let me show a small example. So assume that this is our complete binary tree. So in this case, n is equal to 10 and the number of levels L is equal to 4. Well, let's first do the following thing. Let's complete the last level. And let's denote the resulting number of nodes by n prime. In this case, in particular, the number of nodes in the new tree is equal to 15. Well, the first thing to note is that n prime is at most 2n. Well, this is just because in such a tree where all levels, including the last one, are fully packed, the number of nodes on each level is equal to the number of nodes on all the previous levels minus 1. Okay, so for example, here the number of levels on the last level is 8, and the number of nodes on all previous levels is 7. So we added at most 7 vertices. Now, when we have such a tree where all the levels are packed completely, it is easy to relate the number of levels with the number of vertices, namely with the number of nodes. Namely, n prime is equal to 2 to the L minus 1. This allows us to conclude that L is equal to binary logarithm of n prime plus 1. Now, recall that n prime is at most 2n, which allows us to write that L is at most binary logarithm of 2n plus 1, which is of course big O of just log n. The second advantage of complete binary trees is not so straightforward, but fortunately it is still easy to describe. To explain it, let's consider again a toy example. I mean a complete binary tree shown here on the slide. Let's enumerate all its nodes going from top to down and on each level from left to right. So this way the root receives number 1, to its children receive numbers 2 and 3, and so on. So it turns out that such a numbering allows for each vertex number I, for example, to be specific, to compute the number of its parent and the numbers of its children using the following simple formulas. Once again, if we have a node number I, then its parent has number I divided by 2 and rounded down, while its two children have numbers 2i and 2i plus 1. To give a specific example, assume that I is equal to 4, which means that we are speaking about this node. Then, to find out the number of its parent, we need to divide I by 2. This gives us 2. and indeed vertex number 2 is a parent of vertex number 4, while to find out the numbers of two children of this node, we need to multiply I by 2. This gives us this node, and multiply I by 2 and add 1, and this gives us this node. And these two nodes are indeed children of vertex number 4, right? And this is very convenient. This allows us to store the whole complete binary tree just in an array. So we do not need to store any links for each vertex to its parent and to its two children. So these links can be computed just on the fly. Again, to give a concrete example, assume that we are talking about vertex number 3. So in this case, I is equal to 3. To find out the number of its parent, we just divide I by 2 and round down. So this gives us vertex number 1, and indeed vertex number 1 is the parent of the vertex number 3. And to find out the numbers of its two children, we just multiply I by 2 and also multiply I by 2 and add 1. This gives us, in this case, vertices number 6 and vertex number 7. So, and we know its indices in the array. Okay, we've just discussed two advantages of complete binary trees. And it would be too optimistic to expect that these advantages come to us at no cost. So we need to pay something. And our cost is that we need to keep the tree complete, right? We need to ensure that at each point of time our binary tree is complete. Well, to ensure this, let's just ask ourselves what operations change the shape of our tree. Essentially, these are only two operations, namely insert and extract max. So two operations, sift up and sift down, they actually do not change the shape of the tree. They just swap some two elements inside the tree. Another operation which actually changes the shape is remove an element. However, it does so by calling the extract max procedure. So in the next on the next slide, we will explain how to modify our insert and extract max operations so that they preserve completeness of our tree. To keep a tree complete when we insert something into a complete binary tree, we just insert the new element as the leaf to the leftmost vacant position on the last level. Well, an example is given here. So we insert element 30 just to the right of the last element on the last level. Okay, then we need to let this new element sift up, so we perform a number of swaps. So 30 is swapped with 14, then still there is a problem, so 30 is greater than 29, so we swap it again. Okay, now the property of the heap is satisfied for all the edges. Well, when we need to extract the maximum value, recall that we first replace the root by some leaf. Well, in this case, to keep the tree complete, let's just select the last leaf at the last level. In this case, it is 14. So we replace 42 with 14, and then again perform a number of swaps required to satisfy the property of the heap. Okay, so in this case, 14 is swapped with 30, and then 14 is swapped with 29. This gives us a correct heap whose underlying tree is a complete binary tree. Well, so far so good. We now know how to maintain the tree complete and how to store it in an array. In the next video, we will show the full pseudocode of the binary max heap data structure.